Lesson 3, Part 1. Let's investigate this special integral from a to infinity of 1 over e to the x dx. So that's going to equal the integral from a to infinity. I'm just going to rewrite it as e to the negative x dx. Okay, so we're going to use the definition of this improper integral. So it's the limit as b goes to infinity of the integral from a to that placer b, e to the negative x dx. And moving along further, this is the limit as b goes to infinity. The antiderivative is going to be negative e to the negative x. And again, we're taking from a to b. So that's going to equal the limit as b goes to infinity of negative e to the negative b minus a minus, so plus e to the negative a. Okay, so this portion of it, because b is going to infinity and it's negative b, this is going to go to 0. And so the limit is going to go e to the negative a, or simply 1 over e to the a. What it converges to is not as important as the fact that it simply converges. So going forward, we're going to say, therefore, just like we had a p integral, we're going to say this different integral from a to infinity of 1 over e to the x dx converges. And again, this is for a greater than 0. It converges, and this is going to be established as the, we'll call it the E integral. You will find this wording nowhere. I made it up. But we're going to use it in some proofs, and again, developing some language that we will use in another chapter when it becomes more important. The E integral, we will call this. Next, we're going to look at the limit comparison test. This limit comparison test hypothesis starts off very similar to the direct comparison test. Number 1, some function f of x and g of x are positive and continuous on some interval a to infinity. In fact, that's identical to the beginning of the direct comparison test. Option 2, or part 2 of the hypothesis. The integral from a to infinity of the g of x dx converges. We would say converges, or we would say diverges, which is also identical to the direct comparison test. Part 3 is where they differ. The limit as x goes to infinity of the ratio of the two functions, f of x over g of x, if that equals c, a real number, so where c is between 0, so bigger than 0, can't equal 0, to infinity. So a c, you could also write c is an element of 0 to infinity, or you can simply say that c is greater than 0. But the fact here is it has a limit. There is a definite limit. In this case, the limit is c. If that's the case, if it has a limit, then with the criteria above, then we would say that the integral from a to infinity of f of x dx converges or diverges the same as the integral from a to infinity of g of x dx. We would say if this limit is equal to c, we would say that they grow at the same rate and therefore they're going to converge together or diverge together when taking the integral. Let's do a proof to illustrate the limit comparison test. Let's prove that the integral from 1 to infinity of 1 over 1 plus x squared dx converges or diverges using this limit comparison test. Please note, this may not be the only test you could use, but it is the test I'm asking you to use here. So first thing, let's let f of x be the integrand 1 over 1 plus x squared, and g of x, like in the direct comparison test, some function that we know whose integral converges or diverges through one of our memorized methods. In this case, I think it's pretty clear to see that it's going to be 1 over x squared. Alright, so step 1. F of x and g of x are positive and continuous on the interval closed 1 to infinity. Step 2, the integral from 1 to infinity of g of x dx is equal to 1 to infinity. Notice how I write it generic first, then 1 over x squared dx. And we know that this converges or diverges. Do you know what this does? You should know that it converges. And by what reasoning? Converges by p integral, where p is equal to 2, which is greater than 1. The p integral. That's what we established in an earlier lesson. Step 3. Here's where we're going to do the limit of the ratio. The limit as x goes to infinity, write it generically, f of x over g of x. That's going to equal the limit as x goes to infinity, 1 over 1 plus x squared over 1 over x squared. Now, if I can simplify the limit as x goes to infinity, multiply reciprocal, and I get x squared over 1 plus x squared. You certainly can employ L'Hopital's rule here, but also you should have this memorized for pre-calculus. The degrees are the same, so the leading coefficient of those terms becomes our limit. So this limit is equal to 1, which is in fact an element of 0 to infinity. So that's good. So what does that mean when the limit exists? The limit is equal to 1. What will that mean? It doesn't mean converge. It doesn't mean diverge. It means it will do the same as g of x stated in part 2. So therefore, now, the integral from 1 to infinity of f of x dx equals the integral from 1 to infinity 1 over 1 plus x squared dx, converges also by the limit comparison test. Example B, prove that the integral from 3 to infinity 1 over e to the x minus 5 dx converges or diverges using the limit comparison test. So we're going to let f of x equal integrand e to the x minus 5, g of x equals, hopefully you would be able to determine that's 1 over e to the x, and we go to our step 1. F and g are positive and continuous on 3 to infinity. Step 2, the integral from 3 to infinity of g of x dx is equal to the integral from 3 to infinity of 1 over e to the x dx. Ah, behold, you've seen this. And what does this do? You should know. Converges. By what reasoning? As the e integral. Now, you may be concerned, well, if I'm making up these names p integral and e integral, what about the AP test? Can I use them? No, not to worry. These exact type of proofs are not on the AP examination. They are just concepts that we will build and help to understand the logic. Next, limit as x goes to infinity of the ratio, which is the limit as x goes to infinity 1 over e to the x minus 5 over 1 over e to the x. limit x goes to infinity, e to the x over e to the x minus 5. And it looks like we have L'Hopital's rule in play here, infinity over infinity. So this is the limit as x goes to infinity of, make that look like an infinity, e to the x over e to the x. And this is the limit as x goes to infinity. See, what happens here is we first simplify this to 1, and then the limit as x varies of a constant 1 is that constant. So the limit here is also equal to 1. Again, I am happy, not that I say that 1 always converges, but I'm happy because it's conclusive. In the limit comparison test, we want conclusive evidence, which will happen when we get a real limit. And it's going to then have the same behavior as g. So therefore, the integral from through to infinity of g of x dx converges also by the limit comparison test. Example C is the same exact integral, and we want to talk about converging or diverging using the direct comparison test. So it would start off the same, let f and g equal. Step 1 is identical, step 2 is identical, and then step 3 is where they differ. So if you know this well, the direct comparison test, we know that the integral of g of x will converge. So we would need to show that f of x is always less than or equal to g of x, and then we would say that it converges also. The problem here is that f of x, which equals 1 over e to the x minus 5, is actually bigger than 1 over e to the x, which is g of x. And that's true on the interval 3 to infinity. So what would this mean in this problem? It wouldn't certainly mean that it diverges. It would mean we have an inconclusive result. And we would say, therefore, the direct comparison test is inconclusive. And we would need to use another test. So had you tried the direct comparison test first, it would have failed. Then you might have tried the limit comparison test, or you may have even tried the definition using limit statements and seeing if the integral by definition converged or diverged.